Hello, my dear students. Let us discuss about effect of eccentric foundation base. So this is a concentric foundation level. So the load is acting exactly at the center. Okay, but in this case, eccentric foundation case, what happens? The load is acting here. Okay, so this is the concentric position and this is eccentric position. So here you have E value. You have to consider while calculating the bearing capacity. Okay, so this is the depth and this is the base of the foundation, but when the load is exactly acting at the center, then it is called as concentric loading. If it is not at the center, then it is eccentric, so you have to consider the effect of E. Okay, so the formula it changes now here. The bearing capacity equation is developed with the idealization that the load on the foundation is concentric. However, the forces on the foundation may be eccentric or foundation may be subjected to additional movement. In such situations, the width of the foundation B shall be considered as follows. B dash equal to B minus 2E. So, while calculating the size of a B dash, you have to consider B minus 2E. Okay, because eccentricity is there, that has to be considered. If the loads are eccentric in both the directions, then B dash is equal to B minus 2EB and L dash is equal to L minus 2EL. If there is only one direction, then only one change. B dash is equal to B minus 2E. But if the loads are eccentric in both the direction, then you have to take B dash and L dash. So B dash is equal to B minus 2EB and L dash is equal to L minus 2EL. Okay. Further, area of foundation to be considered for safe load carried by foundation is not the actual area, but the effective area. That is equal to A dash is equal to B dash into L dash. So, when calculating the area, you have to consider A dash, that is equal to B dash into L dash. In the calculation of bearing capacity, width to be considered as B dash, where B dash is less than L dash. Hence, the effect of provision of eccentric footing is to reduce the bearing capacity and load carrying capacity of the footing. So, this difference you have to consider when there is a eccentric loading. Okay, next let us go for Meyerhoff's analysis. Till now what I have discussed, that is Terzaghi's analysis. Let us see what is Meyerhoff's analysis. Meyerhoff extended the analysis of plastic equilibrium of a surface footing to shallow and deep foundations. That Terzaghi's theory was only for the shallow foundation, but Meyerhoff extended the analysis to the deep foundations also. Figure A and B show the failure mechanism for shallow and deep foundation according to both Terzaghi's and Meyerhoff analysis. This is the figure shown here. This is for shallow foundation. This is for deep foundation. Shallow foundation, this part is Terzaghi's theory and this part is Meyerhoff's theory. Okay, what Meyerhoff's theory says? In the Meyerhoff's analysis, ABD is the elastic zone. Okay, which is ABD? ABD is the elastic zone according to the Meyerhoff, and BDE is the radial shear zone. BDE is the radial shear zone. This portion BDE is the radial shear zone, and BEFG, this portion BEFG is the zone of mixed shear, in which shear varies between radial and plane shear depending largely upon the depth and roughness of the foundation. The plastic equilibrium in these zones can be established from the boundary conditions starting from the foundation shaft. To simplify the analysis, Meyerhoff introduced a parameter B, the angle, to define the line BF. He introduced this angle beta, okay, which is the angle defined the line BF, joining point B to F, where the assumed boundary failure slip line intersects the soil surface. The resultant effects of the wedge of the soil BFG BFG, this portion, BFG, this portion, okay, is represented by the normal and tangential stresses P0 and S0 on B of P0 and S0, okay, that is normal and tangential stresses developed. The plane BF is termed as the equivalent free surface, BF. The frame BF is termed as the equivalent free surface, and P0 and S0 are termed as the equivalent free surface stresses. The angle beta increases with depth and become 90 degree for D foundation. This is about Mehrhof analysis. Okay, so just read it once again, you will understand. Okay, this is Mehrhof's theory for D foundation. Same thing here explained in the single diagram. Here it is compared with the Terzaghi's theory also. Okay. See here, this is ABD is the elastic zone, that is this portion. ABD is the elastic zone, ABD is the elastic zone, and BD is the radial zone, BDE is the radial zone, and BEFG is the zone of mixed zone. BEFG, this is the portion G, is the mixed zone. Okay, so everything is explained, so just go through that. Now he derived his equation to find the ultimate bearing capacity by taking into account the shape, depth and inclination factors. For the vertical load, he considered the shape effect, depth and inclination factors also. So vertical load, for the vertical load he has given this equation. QF is equal to CNC SC DC plus sigma dash is nothing but gamma D NQ SQ DQ plus 0.5 gamma beta N gamma S gamma and D gamma. For the inclined load, he considered the inclination factor. So he just added IC, IQ, I gamma for the first, second, third term respectively. But that means QF is equal to CNC DC IC plus sigma dash NQ DQ IQ plus 0.5 gamma beta N gamma S gamma D gamma. Sorry, here SC also there. Okay, here there will be SC also. Okay, there is SC and here SQ. Only the addition of inclination factors here. Okay, next is here I see. Now NQ is given by can calculate NQ by using this formula, E to the power pi tan phi tan square 45 plus phi by 2. NC is equal to NQ minus 1 cot phi, and gamma is equal to NQ minus 1 tan of 1.4 phi. And also he had given the formula to find the shape factor, depth factor and inclination factors. So this NC, NQ, N gamma can also be available in the table. This is the table. So Mehrhof's bearing capacity factor. There is a slight changing NC, NQ, N gamma when compared with the Terzaghi's analysis. He had given for the different phi values NC, NQ, N gamma values. These are the NC, NQ, N gamma values. Now S a shape factor, D depth factor, I is the inclination factor. So had given SC is equal to 1 plus 0.2 Kp B divided by L, and DC and for phi is equal to 0, SQ S gamma is equal to 1. If phi is greater than or equal to 10, then you have to calculate SQ S gamma is equal to 1 plus 0.1 times of Kp B divided by L. Similarly, for depth factor, DC is equal to 1 plus 0.2 square root of Kp D divided by B. For phi equal to 0, dq d gamma equal to 1. But for phi greater than or equal to 10, this is the formula. For the inclination factor, IC equal to IQ equal to 1 minus alpha divided by 90 degree, and I gamma is equal to 1 minus alpha divided by phi whole square. Alpha is equal to angle of resultant measured from vertical axis. Kp is equal to tan square of 45 plus 5 by 2. So this is about Mehra's theory, and also it may be noted that bearing capacity equations have been derived treating the problem as a plane strain problem. So he gave the equation to obtain phi is equal to 1.1 minus zero point 0.1 into B divided by L of phi triaxial. Okay, so this is about Mehra's theory. You just remember these table values. I mean, no need to remember. You should know to refer for the different phi values, and these are the S shape factors formula. And for if phi is equal to 0, you can directly take it as 1. If phi is greater than or equal to 10, you have to use this formula. Similarly, for the depth factor and as well as for the inclination factor also. And then these are the equations for the vertical load and for the inclined load. Okay, this is about Mehra's theory. He had given theory, derived the equation for both deep foundation as well as shallow foundation. I hope all of you understood. Just go through this again and again, you will understand. Thank you.